In this lesson, we will study two more categories of probabilities. Those are not and or probabilities, and we'll also see how those relate to odds. Let's start with not probabilities, and we'll motivate that with example 1. This says a six-sided die is rolled once. Find the probability of rolling a 1, then find the probability of not rolling a 1. To solve this, I'm going to list out the sample space. So if you roll a six-sided die, there are 6 things that can happen. You can roll a 1, 2, a 3, a 4, a 5, and a 6. Next, I'll define this event here, rolling a 1, as E. So if E is rolling a 1, that means we're talking about the subset of the number 1. If we want to know the probability that event E happens, it is the number of things in this event divided by the number of things in the sample space. That is 1 out of 6 things, and that actually is the answer. It is 1/6, and I'll leave it as an exact fraction for the probability. You can also answer this just by looking at the sample space itself. This is the event, and so it's 1 out of the 6 things, and that's why the probability is 1/6. Now on to the second part of this example. It then says, find the probability of the event not rolling a 1. So that means not this thing. You can write this as not E. So what is that thing? Well, if you didn't roll a 1, that means you could have rolled a 2, a 3, a 4, 5, or a 6. So in fact, this is not E. It is this subset of the sample space. It's a 2, a 3, a 4, a 5, or a 6. To say not this in this set means everything else. So that is this stuff. It's this part of the sample space. And this creates a nice connection between an event and not that event. It's just everything that was not covered in this event. So on to the probability of not E. What is that? The probability of not E. Well, it's this number of things, which there are 5, out of the entire sample space, which has size 6. So this is 5/6. There we go. So we have E and not E. The important observation to make is if you consider an event and then not that event, you actually are talking about the entire sample space. You can see that if you take the probability of E and you add it to the probability of not E, you get something that's not very surprising. The event E was a 1/6. The event of not E was everything else, so it was 5 out of 6. If you add those two things together, you add the numerators, which is 6 out of 6, and this reduces to 1, which if you convert to a percent is 100%. So E and not E account for every possible thing that can happen. So if you add these two things together, and we're talking about probabilities, that's equal to 1. And this takes us to a formula for dealing with not probabilities. For any event E, we have the following. The probability that not E happens is equivalent to saying 1 minus the probability that E happens. Why is this true? Let's just go back to this really quick. If you sum these two things together, no matter what the event is, it has to equal 1. So from that connection, we saw that the probability of E plus the probability of not E always equals 1. You're saying that accounts for 100% of what can happen. If you want to solve for the probability of not E, you can subtract the probability of E to the other side of the equation. So essentially, you're just taking the number for the probability of E, whatever it is equal to, and you are subtracting it from both sides. And what you have is that the probability of not E is simply 1 minus the probability of E. And that is where this formula comes from here. So if you know the probability of E, you actually don't have to go through all this work to figure out the probability of not E. We could have gotten to this number almost immediately once we figured this out. Here's what that would have looked like. We found the probability of E. You want to know the probability of not E. What you would do is you'd say, okay, to find the probability of not E, we'll just take 1 and we'll subtract off a 1/6. If you want to subtract this, you need a common denominator. 1 is equivalent to 6 over 6, so that's 6 over 6 minus 1 over 6. And if you subtract the numerators, 6 minus 1 is 5, and we do get our answer of 5 over 6. So this thing matches up with this. So it's kind of a nice shortcut here where if you know one probability, then you can find the other. Note also that the probability of E is equal to 1 minus the probability of not E. This is true as well. And the way you can show that this is true is by taking this equation. You don't subtract this from both sides. You subtract this to the other side, meaning it will be on this side of the equation. So we actually have two formulas. There's this one, and there is this one here. The thing to keep in mind is what this formula is saying is the probability of not E and the probability of E add up to 100% of what can happen. Let's try out this not probability formula here in example 2. We are told one card is dealt from a shuffled 52 card deck. What is the probability of not being dealt a heart? One approach that you could take here is, we saw that the probability of not the event E is equivalent to 1 minus the probability of event E. Sometimes it's easier to think of an event instead of putting a not in front of it. To solve for this part of the problem using this formula, we will define an event E and then solve for the probability of not E using this formula. So what is my event going to be equal to? The event I will choose is being dealt a heart. So this is being dealt a heart. And what we really care about is the number of things in this event. So if you have these 52 cards, so that's the sample space, we know that has a size of 52. How many ways can you be dealt a heart? Well, it's all of these things here, which we know there are 13. Therefore, if you want the probability of event E, it's the number of hearts that you could possibly be dealt, which there are 13, out of the size of the sample space, which is 52 cards. And we've seen before that this reduces to 1/4. There are 4 total suits, and we're saying you can get the entirety of one of those suits. So 1/4 or 0.25. Now the question is, what is the probability of not this happening? Not E means you are dealt, well, not a heart, but a spade, a diamond, or a club. So it's all those possibilities. If we use this formula to figure out that probability, the probability of not E is simply 1 minus 1/4, which is 4/4 minus 1/4. 4/4 and 1 are the same thing. So the probability of not E, completely simplified, is 3/4 after you subtract the numerators. That's it. So E happens 25% of the time, and not E occurs 75% of the time. But that makes sense. I mean, 3 out of the 4 suits is not E, so I was expecting 3/4. Now that is the first part of example 2. The second 2 questions ask, what are the odds in favor of being dealt a heart? And what are the odds against being dealt a heart? And so here we're introducing a new term, and that is odds. Down here I have the definition. So there's 2 definitions, one for odds in favor and one for odds against. Odds in favor of event E occurring, it works a lot like probability, except it's not the part over the whole, it's the part that it happens versus the part that it does not happen. The definition is a bit confusing, so I say we use these numbers to compute it and then try to make some sense of that. So let's first do odds in favor of event E occurring. So this means, what are the odds that you are dealt a heart from a well-shuffled deck? Well, according to this thing, we'll take the probability of E happening and we're going to divide it by the probability of E not happening. So it's this fraction divided by this fraction. So we'll have to divide fractions, but I first want to do odds in favor of event E. This is the fraction 1/4 divided by 3/4. And if you recall how to divide two fractions, you could also write it like this. This is 1/4 divided by 3/4. The way this is done is by flipping the second fraction and changing this to multiplication. So this is really 1/4 times 4/3. And thankfully, this kind of turns into an easy problem because we can cancel those 4s and they both become 1s. And what we're left over is with a 1 in the top and a 3 in the bottom. So here are the odds in favor of event E occurring. This number in the top corresponds to the numerator of the fraction in the definition. So for every one time that it does happen, 3 times it does not happen. Often odds are not expressed as fractions. Instead, they're written as 1 colon and then 3 in this example, and you'd say the odds in favor of event E happening are 1 to 3. The 1 means how many times event E will happen, and the 3 means how many times that it will not happen. This is very different than the fraction in a probability. When you talk about a probability, this is how many times that it happens out of the total number of times. But here, this is saying for every one time that you get a heart, 3 times you will not get a heart. And so that's the difference between odds and probabilities. Now, this was odds in favor of event E happening. Well, what are the odds against event E happening? I say we plug it into this formula, and I bet you will not be surprised by the answer, but I'll put it down here. So what about odds against? To compute that using this formula, it's the same definition, but the fraction is flipped. Since the emphasis is on the against, meaning E does not happen, you put the probability that E does not happen on top, but the probability that E does happen on the bottom. So my starting point would look like not E, which we saw was 3/4, and that's divided by E happening, which is 1/4. Of course, you could write this as 3/4 divided by 1/4, and as we stated, this is computed by changing to multiplication and then flipping the second fraction. Here, well, actually the same thing happens. The 4's cancel, and we're left with the fraction 3/1. If you write this as odds, you would express this as 3 to 1. So what are the odds against being dealt a heart? They're not 1 to 3. It's just reversed. It's 3 to 1. This will happen every single time when you go from in favor to against. You just reverse these two numbers. It's just important to note that this means when you say 3 to 1, and we're talking about against, for every 3 times that you don't get a heart, 1 time you will be dealt a heart. So odds and probability are very similar. The difference is within the definition itself. In the denominator, you're not dividing by the probability of the sample space. It's either the probability of E or the probability of not E, depending on if you're talking about in favor or against. Let's move on to the category of or formulas. And there's 2 cases to consider. And we'll start with this first one here where E1 and E2 are mutually exclusive, meaning they have nothing in common with one another. The way this probability is read is the probability that E1 or E2 occurs. I think I'll first state the formula and then we'll discuss why it is true using example 3. If the 2 events have nothing in common and you want to know the probability that one or the other happens, the way you find it is by taking the probability of the first event and then adding it to the probability of the second event. So now moving on to example 3. It says that one card is dealt from a shuffled 52 card deck. What is the probability of being dealt a 7 or a queen? So when I look at this probability, E1 is the event being dealt a 7, and E2 is the event being dealt a queen. So for this one here, I'll write, okay, that's E1, and this thing here I'll call E2. And what we're looking for is the probability that E1 or E2 occurs. The way you find it is by finding the number of cases where that happens up here and then dividing it by the number of things in the entire sample space. So I'm actually going to highlight this event on these cards. If you're dealt a 7, we are talking about any one of these 4 choices. So there's 4 ways that can happen. At the same time, there are 4 ways that you can be dealt a queen. So when we say this event, we're talking about the number of things that happened in the event, which there are a total of 8 of. These are mutually exclusive events because these 4 and these 4 have nothing in common. So if you want to find this probability, using the above diagram, we have 4 here, we have 4 here. That gives us a total of 4 plus 4, or 8 things. And this is divided by 52. And then I can add the 4s. We get 8 over 52, and that reduces to a probability of 2 over 13, and that is the answer. And really, we didn't even refer back to this formula whatsoever. I literally just knew there were 52 things in the entire sample space, and if we say this or this happens, we're saying, oh, well, there's a total of 8 things that occur. Notice that you could go directly to this formula. What that would look like in this case is, well, the probability that event 1 happens is 4 out of 52. And then the probability that event 2 happens, it's also 4 out of 52. And to add fractions, you add the numerators. And notice we're just really doing the same thing down here. Going directly to the formula, again, we get 8 over 52, which also reduces to 2 over 13. So the formula actually matches up with the intuition. So when these events have nothing in common, when you're adding the 2 probabilities, what that's really doing in the fraction is just counting up the number of ways that both occur. And that's what this formula means. All right, let's try this again. There's another part. It says find the probability of being dealt the ace of spades and a heart. Okay, so I'll use an E1 and an E2. I'll use a different color here. So say E1 is being dealt the ace of spades, and E2 is being dealt a heart. All right, so to start with, the probability that E1 occurs, to figure that out, you can go to the deck of cards and say, being dealt an ace of spades means this is happening within your sample space. And then being dealt a heart. Now here I'm ignoring the blue just because that was in the first part of this problem. If you focus on just the red, being dealt a heart means this happens. So this stuff here. Are these events mutually exclusive? Yeah, these 2 separate things never interact with each other. They're completely separate. And therefore, you can apply this formula to find the probability. Let's do that. The probability that E1 or E2 occurs is the probability that E1 happens plus the probability that E2 happens. The probability of E1 is, there's exactly one way this occurs. That is 1 out of the total 52. And then the way E2 happens is, well, there's 13 out of 52 ways that can happen. So that's 13 out of 52. These can be added together. You're basically just counting up the number of ways out of 52 this event happens. That's 14. And we can reduce 14 over 52 because they both can be divided by 2. 52 divided by 2 is 26. This is 7 over 26, and that is the probability. So to recap, what this formula is saying is when you want to find the probability of 2 mutually exclusive events, addition is used in the formula because that's how you count things. if you have this many of one category and this many of another, the total amount that you have will be the sum of those two things. All right, so now there's a final question here. Let's see if something different happens. It says find the probability of being dealt an ace or a heart. So we're looking at this part of the problem now. And okay, I'll let E1, that will be the event being dealt an ace. It could be any ace. And then E2 is being dealt a heart. And if we highlight those things, let's highlight it. Okay, if you are dealt an ace, again, I'm ignoring the red and the blue. We're talking about, here are 4 ways that this can happen. So the probability of event E1 is 4 over 52. Being dealt a heart, so I'm going to highlight over this red portion here. Again, ignoring the red. So here we go. We could be dealt any one of these things, which there are 13 out of 52. So if we want the probability that E1 or E2 happens, if we use the above formula, it's going to be the probability of E1 plus the probability of E2. I'll continue this work down here. We know the probability of E1, that is 4 out of 52. And we also know the probability of E2, that is 13 out of 52. And if you add those together, you get 17 out of 52. So what we did here was use this formula to get to this number here. So what do you think? Did it work or did it not? This actually is the wrong answer. What went wrong here? What goes wrong is this right here. These two events are not mutually exclusive. They have an overlap, exactly this spot right here. To apply this formula, if you're counting, you only want to count the highlighted things once. But if you add this number to this number, you have not counted this spot once. You actually counted it twice. I mean, this answer is very, very close to the correct answer. If you want to adjust it, you just want to take away the fact that this was doubled, that you counted it twice. So to fix this, you can subtract 1 out of 52. Now, the reason for this is because, again, these had something in common, exactly one thing in common, which is why I took one thing away. And when you do that, it does take you to the correct answer of 16 out of 52, which we can simplify to 4 out of 13. So I'll get rid of that. 4 out of 13. And that is the correct answer here. So here's the thing to notice. When you're finding an OR probability, sometimes you can just add the probabilities together because that's counting the total number of ways that these events can occur, unless they have something in common. If they have something in common, then you just want to subtract out the fact that you counted things twice. We'll state this more carefully in a formula on the next slide. So here is the general formula for OR. So if the events E1 and E2 are mutually exclusive or not, it's basically the same thing. It's the sum of the two probabilities, E1 and E2, but you want to subtract off anything they have in common. And the way you would express that is E1 and E2. So if you think about the example we just looked at on the previous slide, we had that E1 was being dealt an ace, and then E2 was being dealt a heart. And if you look at E1 and E2, how can you be dealt an ace and a heart at the same time? Well, that's if you're dealt the ace of hearts. And the probability that this event occurs, well, there's only one ace of hearts out of 52 possible cards, and that's exactly what we subtracted off at the end in the previous example. So, when dealing with an or probability, it's good to ask yourself, do you think the events are mutually exclusive or not? If they are mutually exclusive, that's great. You can just add the probabilities. If they have something in common, you have to figure out what that is and then subtract off that probability. Let's try this in example 4. We are told a six-sided die is rolled once, and I'll state the sample space for this. That's a 1, a 2, 3, 4, a 5, or a 6 that can be rolled, so those are your options. The first part looks simple. What is the probability of rolling an even number? So I'll call this E1. Well, if you're rolling an even number, so just one roll, it could be a 2, 4, or a 6. We're just counting things here in the sample space. The size, the number of things in the sample space is 3, and therefore the probability of E1 occurring is 3 things out of the total of 6, or 1/2 of the time. All right, part B says rolling a number greater than 2. I guess I'll call this E2. If you roll something that's greater than 2, it could be a 3 through 6. That is 4 possible things that could happen. And so if you want the probability of this, the probability of E2, that's 4 out of 6 things. And if you cancel a factor of 2, you get 2/3. There we go. That's the probability of rolling a number greater than 2, 2/3. Here we have rolling an even number and a number greater than 2. So this time, we want the probability of E1 and E2. What's that equal to? Here we're using the same E1 and E2 that were in parts A and B. I think off to the side here, I'll put, well, what's the number of things in this event of being even and greater than 2 at the same time? Well, if you're greater than 2, you can only focus on these 4 choices, and of those, exactly 2 are even. The actual set is the numbers 4 and 6, but what I care about is how many things are there. That's a total of 2 things. Therefore, the probability of E1 and E2 occurring means there's 2 out of the 6 possible ways it could happen, and that is 1 out of 3 when you reduce it. Okay, so we got a half, 2/3, and 1/3. For part D, we have rolling an even number or. Okay, so here we have this or, meaning we have to use one of the formulas that we developed. Rolling an even number or a number greater than 2. So for this one, I'm looking for the probability of E1 or E2. Are these events E1 and E2 mutually exclusive? No. They have stuff in common. An even number is 2, 4, or 6. Greater than 2 is 3, 4, 5, or 6. There's stuff in E1 and E2 that are common. These are not mutually exclusive. I want to use this formula here. But thankfully, we actually have all the numbers we need using parts A, B, and C. Part A was the probability of E1. Part B was the probability of E2. And then in part C, we already found what the probability of those 2 things in common are. So to get this answer, I'm going to go directly to the formula. I'm going to say, well, I'll first count the number of ways that can happen for E1. Its corresponding probability is a half. To that, I will add the probability of E2. We got that that was 2/3. But because they have things in common, if we simply count these 2 things, we've counted too much stuff, and we need to subtract some of it. The amount that you subtract is the overlap, which is 1/3. Here it is. If we can simplify this down to a single number, we'll have our answer. I'm going to use a common denominator of 6. So if I look at these fractions, you can think of them all as something over 6. A half is 3 over 6. 2/3, if we multiply by 2 in the top and bottom, we get 4 over 6. And then if we double the 3 and the 1, we get 2 over 6. This is really 3 over 6 plus 4 over 6 minus 2 over 6. Written this way, 3 plus 4 is 7 minus 2 is 5 with our common denominator of 6. This is the answer to rolling an even number or a number greater than 2. In our last example, since we've talked about probability and odds, let's try to make a connection between those two things. We are told one card is randomly drawn from a shuffled 52 card deck. Part A says, find the odds in favor of drawing a king. For this one here, I'm going to let E represent this event. Maybe I'll call it E1. So that's the event that you draw a king. If you're talking about odds in favor, if you remember, it is this fraction. So when you say odds in favor, we mean the probability that it does happen compared to the probability that it does not happen. Let's compute those two things. What is the probability that you will draw a king? Well, there are 4 total kings out of 52 possible cards. And when we reduce this is 1 over 13, which is our probability. The probability of not E1 occurring, well, that's going to be everything else, but we saw you can do 1 minus. We could do either one of these numbers. I'll choose 1 over 13, and I'll write 1 as 13 over 13. And when you subtract the numerators, 1 from 13 is 12. That's 12 over 13. And that makes sense in terms of this formula. If you add these two events together, that should equal 1 or 100%. 1 out of 13 plus 12 out of 13 is 13 out of 13. 1, 100%. To find the odds in favor, we divide this number to this number. To speed this up a little bit, what we saw is you can take the fraction 1 over 13 and divide by 12 over 13. To divide two fractions, you flip and multiply, meaning you flip the second fraction. And the 13s nicely cancel. And what we're left with here is the fraction 1 over 12. So here it is. This is the odds in favor of being dealt a king. We would state these odds as 1 to 12. So for every 1 time that it does happen, the in favor, 12 times it will not. Now, there's a second part of this problem, which technically we already did. But the point of this is if you start with odds, how would you go backwards to get the probability? If you want the probability of drawing a king, that's the total number of ways that it does happen out of all possibilities. And all possibilities can be computed by adding 1 to 12. So if you have odds and you want to go to probability, so to work backwards, the probability of E1 is the number of times that it happens, which is 1, it's this very first number here, divided by the total number of ways it can occur. That means both it doesn't happen and it does. It's the sum of those two numbers, 1 plus 12. And that probability is 1 over 13, which is important to point out is in fact equal to this number here. In part B, it says find the odds against drawing a red jack. So this time, since we're talking about odds against, we're talking about the probability that the event doesn't occur divided by the probability that the event does occur. So basically, we are flipping this fraction. I will call the event drawing a red jack E2. The probability that E2 occurs is, well, there's 4 total jacks and 2 of them are red, and that's out of 52 possible cards. This reduces to 1 over 26. If we want the probability that not E2 occurs, that is, well, it's 1 minus 1 over 26. 1 is the same thing as 26 over 26. And if we take 1 over 26 from that, we get 25 over 26, which makes sense. If we add this and this together, we get 26 over 26, which is 1, or 100%. So, what are the odds that this event occurs? It is now this number divided by this number, so we're dividing these two fractions. That is 25 over 26 divided by 1 over 26. To divide, we change to multiplication and flip the second fraction, which works out great because the 26's cancel. And what is left over is 25 over 1. We'd say the odds are 25 to 1, meaning 25 times it does not happen and 1 time it does happen. In total, that's 26 times, but this many times it doesn't, this many times it does. Was the probability of not drawing a jack? We technically already know the answer, but again, the point in this question is, if you know the odds, how do you go from the odds to the probability of not E2? You would take the number of times that it doesn't happen, which we know is 25, and you divide it by the total number of ways that it can happen. So that's actually 25 plus 1. And when you add the two numbers in the denominator, that is 26. So here, it matches up with 25 over 26, and we have the correct answer.